look at derivatives of vector-valued functions. Let's suppose we have some vector-valued function. This is defined by xt times my I vector plus yt times my j vector plus z of t times my k vector. The derivative, r prime, of this works exactly the way we want it to. I can take the derivative of individual pieces. So I have x prime times I, y prime times j, and z prime times k, provided that x, y, and z are differentiable at the point t. As our first example, let's consider r of t equal to cosine t sine t e to the t. So my derivative, r prime, I take the derivative of individual pieces. The derivative of cosine is negative sine. The derivative of sine is cosine. And the derivative of e to the t is e to the t. So now I have the derivative of my vector. For my next one, r of t is equal to t cubed minus 4t, ln of t, t over t plus 1. So the derivative, I take the derivative of the first piece. The derivative of t cubed is 3t squared. And the derivative of negative 4t is negative 4. Derivative of the second piece, the derivative of ln of t is 1 over t. And the derivative of the third piece. This is a quotient rule problem, so we need the derivative of the top times the bottom minus the top times derivative of the bottom over the bottom squared. And you can absolutely simplify this third coordinate. I'm not going to do it here, but you can work to simplify this. Next, let's find the direction of the tangent vector at t equal to 0 of this vector-valued function. For the tangent vector, we need to start by actually taking the derivative. For this first piece, that's a product, so I need the product rule. That says the first times derivative of the second plus derivative of the first times the second. The derivative of cosine of 3t is negative 3 sine of 3t. And for my last one, the derivative of ln is 1 over t squared plus 1, but we do need to use the chain rule and multiply by the derivative of the inside, which is 2t. Now that I have this, I can plug in 0. 7 times 0 times e to the t is 0, plus 7 e to the 0. This is negative 3 sine of 0, and 1 over 0 plus 1, 2 times 0. E to the 0 is 1, so this first piece is 7. Sine of 0 is 0, and since 2 times 0 is 0, this whole third component would be 0. So the direction of my tangent vector at this particular point is 7, 0, 0. There are some basic properties of the derivative that we have. First, the derivative of a sum, r of t plus s of t. This works exactly the way it does in single variable calculus, r prime plus s prime. If I split this up over addition, I can just take the derivative of individual pieces. My next one, what happens if I multiply my vector-valued function by a standard function? Well, this follows the chain rule. I can do f of t times r prime of t plus f prime of t times r of t. Next up, With two vectors, I can take their dot product. So let's see how the derivative affects the dot product. And it turns out that taking the derivative of a dot product also satisfies the chain rule. So I can do r of t dot s prime of t plus r prime of t dot s of t. The other type of product I could look at is a cross product. R of s cross s of t. And it turns out this also follows the product rule. R of t crossed with s prime of t plus r prime of t crossed with s of t.